Right, so I decided I wanted to check these original capacitor. Now, a few years ago, I built this H-bridge. Anyone that doesn't know what a H-bridge is, it's a DC to AC converter, and this worked. I used this circuit board I built myself to drive my experimental power supply units, which I was working on, to do with magnetic pulse switching, Alnico magnetic polarization switching. Well, switch the polarity of magnets, the Alnico magnets anyway. You can't do that with others really, without a lot of difficulty. But anyway, so this is set at currently. It produces a high voltage as well. There's two circuits on here. There's one that the H bridge is. Oh, let me just see if I can get you a closer look. Just a minute. It's not very easy to show you. Right. So the H bridge is this top section here, right? I actually outlined it when I did the circuit board. I designed it and I printed the toner transfer system to transfer. These are opto-isolators. All these opto-isolators to isolate any of the pulses, DC feedback, from interfering with the oscillator circuit, which is using that microchip there. I have forgotten the name of it. I've forgotten the number on it now. But it's a driver chip for. Let me see if I can get the light on it right, so you can see what it says. I've got the number now. I've got the circuit diagram I originally designed for it somewhere. When you get the light on it in the right way, you can read it. Yeah, I can't read it properly at the moment. Let me just try, see if I can see it on my computer. Full screen preview. Oh, yeah, it's the TA, yes, I'm like, hang on, damn it, I've drifted, where the hell am I? Right, so if I pan out of it, back out of it. Anyway, never mind about all that. What am I doing? I'm distracting myself again. The whole point of this is the high voltage circuit, which let's get this on here. The high voltage circuit which I built on this side. I'm not even going to worry about the output side, which is the AC part, which is these two wires. What I'm interested in is the high voltage side, this part here, and that generated the high voltage for these capacitors and the output. I want to use that high voltage part to put power into the crappy capacitor, which is the faulty one, and the new capacitor, which is a good one, right? Because I want to measure the loss, the voltage loss. When you charge these up, I also want to try to reform this one a bit. But there's a problem. This thing's been sat for so long, I'm not even sure it's that I'm going to actually get the voltages coming out that I want right now. I'll have to check something. So let me go and get those clips leads off the other meter thing. Because I can use these. I can use these leads off my digital just a minute, let's see if I can bring you around here a bit. I don't know, the charge lead's the wire's a bit short. See if I can get you zoomed in a bit better. Okay, let's see. Oh, it's too much I think. Right, so the output for the high voltage part, which actually the maximum is 100 volts for this, right? Maximum output. And the reason I've thought about using this is because the impedance of this output circuit is quite high, which means if there's any leakage in these capacitors, the old capacitor, if it leaks down too much, we'll see a low voltage on that. Which is great because it means I can actually test these capacitors for higher voltage, because normally I don't have 100 volts kicking about. Now these are supposed to work up to 400 volts, right? They're supposed to run up to 400 volt, but I haven't got 400 volt kicking about. It's a bit it's a bit dangerous having 400 volts lying around. So if I can plug these and get my oscillator to run at the right frequency, I should be able to get a good decent output, high voltage output. And I'm going to clip these on. Now I can't remember now if I've got a diode blocker in here. You know, a diode blocker is something where you can inject high voltage in, but the high voltage can't come out, right? If I remember rightly, high voltage should come out of here anyway, right? Because, yeah, because this was supplying, well, this was supposed to be, the high voltage going in were the voltages which were actually shunted across these yellow and purple wire, right? Through the H bridge, right? For switching. So the H bridge was switching those high voltages. So this is normally for injecting voltages in. Sorry about my audio out of sync on the last video. I've had to make it private temporarily until I can fix the audio sync on it. I'm probably going to download that and re-edit it and re-upload it at some point. But the audio is way out of sync. So let's just clip these on, screw these down. I don't have to, you don't have to be tight. You don't want to bend the pins on it, obviously. I just want to clip this on to this capacitor. Let's see, are we zoomed out? Oh, yeah. I'll just increase the height a bit. So, right, if I clip, now this is important. The polarity is important, so I'm going to just check this. Let's switch it on. Right. So I should. Is it? I've got it right way around. Oh, my meter's turned off. Let's just move them out of the way a minute. There's my meter. Right, I think I've got this right way around. Yeah, but the voltage is really low, 4.1, that's ridiculous. I don't want that, that's no good. I've got it right way around though. Now I need to, oh, excuse me. Right, I need to, where's my screwdriver gone? I just put it down somewhere. Oh, there you are. Right, I need to adjust the oscillator because the voltages are just too low right now. Right, let's just check. Get this meter connected to that. Let me just like, oh, what the hell was that? Oh, yeah, a bit of ferrite was stuck to my screwdriver, magnetised. Right, let's adjust the oscillator. I should be able to get this to, I'm not sure if my battery, I'm using a 24 volt input to run this. Oh, my battery's flat. It's dying, look. It's dimming, look. The 24 volt input voltage is, my nickel metal hydride batteries are flat. That explains why I'm not getting anything out. This thing needs 24 volts, otherwise it doesn't work. So the nickel metal hydride batteries are these things here, right? And they're flat. Yeah. Now what do I do? Oh, I'll get some of my lithium ion batteries and wire them in parallel. That's what I can do. So unplug that, because this thing is as fat as a fart. I haven't charged it up for a couple of years. It's been sat there for a couple of years and it's run down. It wants charging again. Let's find something else. Right, hang on a minute. Right, so if I put these two batteries in series, I should be able to get, what, 20, well these are 11.1 volts, right? So we should be able to get 22.2 volts. Should be enough. Should be enough. Let's get some leads. These leads are covered in dust. I haven't done any electronics for ages. Right, so I haven't really done anything properly. I've been so busy with other stuff. Second Life has been a nice distraction, but one or two people have said, "Oh, I'm glad you're getting back into electronics." Oh my god, look at dust on here. Jesus. Right, so if I plug that white wire onto there, that's positive. I need to check the voltage on here. Actually, let me just do that now. Let me just move that out of the way a bit. Let's see what I've, make sure these batteries are actually equal, because so that's negative. Got a steel washer sticking out the back of here. Right, that's negative. That's this one. That should be, oh, slipping off here. What are we at? Damn it, can't keep it on. Oh, I'll just clip it on this lead. You do. Right, what's this one? What? I'm on DC or AC? 12.2. Good. That's 12.2 volts. And what's this one? So we should get 24, which is what I want. That's 11.1. Alright, let me find another 12.2 one. If I think I've got one. I want to get 24 volts if I can. Let's see. I think when I say recent, I mean probably last year. I think I recently charged these up last year. But lithium ion stores power forever. Once you don't discharge it, that is. Oh, hang on. I'll clip the lead on positive. Let's see what this one is. Are you 12? Oops, stay down. 12.2, yeah, good. So these two in series should give me 24 volt. Exactly, which is what I want. Okay, that's the wrong way around, because positive is at that end, so I want negative at that end. I want to clip this white wire onto here. Hang that wire somewhere out the way, so it doesn't get right. So now I should have 24 volts at this end. At this end here. Right, let's have a look. Yes, we have 24 volts. That's what I want. Okay, 24 volts. Now, if I connect my cigarette lighter thing. I'm going to have to use the clips on here because I haven't got another socket. So I mounted that socket onto them NiCad batteries, right? So right, that's clipped on. That's ground. Clip that on ground. I'm going to do a current measurement to make sure I don't blow anything up, because I think I've wired it right. Pretty sure I did. So put that on current. 200 milliamp range. We're going to connect that one to that little bobbly thing, and this to positive. Let's check current surge. Oh yes, that works. Brilliant. Yeah, we're in business. Yeah, nice and bright. So let's use quite a bit of power, this circuit. It's over 200 milliamps. It's about half an amp to an amp. Let's put it on amp gauge, see what current we're using on amps. Because you remember, when you're stepping voltage up, when you're stepping the voltage up from low voltage to high voltage, you always get quite a high current on the low end. Right, we're on 20 amp, 110 amp range. Let's check, because I'm getting so old that I make mistakes. That's why I have to double check myself over and over again. Right, what are we at? We're using 190 milliamps. Right. Okay, brilliant. So we're going to be able to use that. Right, let's put that all back the way it was. I always, you know, for those who are interested, how comes I've had these meters since in the 1980s and I've never blown them up? Because I have a habit of leaving them all on voltages. Always park them in voltages, because that way, on a high voltage like 200 volt, you're less chance of accidentally connecting it to a power supply. You don't leave it on arms, trust me. That's how you blow your meters. Right, so okay, move that out of the way. I want positive on here. I use a yellow wire. Connect that to that. We have action. Right. Let's check now to see what voltages we've got coming out on here. Turn it on. I'm hoping we get around 80 volts or something. Oh, we have 74 volts. 74 volts is not perfect. Let me tweak this to get the maximum voltage out of here. I have to tweak the oscillator, which is the bottom corner down here. Let's see if we can peak that. See if we can peak it to, oh, we're going down because my oscillator circuit is, it was already peaked at about 80 volts, which is probably the maximum I can get out of it, because these capacitors in series, each one of these capacitors down here is at 50 volts. You can't drive it above 100. 80 volts is probably the maximum I can get out of this. Now, so double checking the polarity. Look, it's going up still, look. That's because of leakage. These capacitors that are on this board are actually on here. They're charging, they're reforming, they're charging. Let's check what we're at now, 82, it's still going up, 82.3, it's going up still. They're actually reforming. Good news. So now what I need to do, very carefully, because these wires down here, these dangly wires down here, oh, you can't see them. Oh shit, my charge lead's too short. I can't move it. I've got my phone on charge right now, because when I'm doing live streams, what have I done? When I'm doing videos, the Streamlabs eats up my battery really fast, so okay, right, the dangly wires that are down here, I have to be careful I don't touch them together, because I want to connect it to, well, I'll switch it off first for safety. Off. Alright, let's check, see how fast that power dissipates on here. Oh, I can't do this. It's dropped to 70 volts, it's dropping. See over there? 69. I don't have sparks, you know what I mean? So I'm gonna let it drop because that power is normally shunted out through the H bridge, through the MOSFETs, to drive circuits. And it's quite a big bang, because these two 1000 microfarad capacitors, there's a lot of blue tag on the top of it, by the way, so ignore that. I've got a 1000 microfarad here and 1000 microfarad here, and they're both in series. So that's together, that is 500 microfarad at 80 volt, which is a lot. I've got to wait for them to discharge. The other way to discharge it is to put a resistor across the here, like, you know. But I am patient, but I want to get these capacitors hooked up. This is a bad one, and I'm interested in the leakage, the leak down. So we're probably going to see a spark when I connect this up. So negative is the black one. I don't know if these little wires can take that current surge. I have no idea. I don't want to fry my circuit. I'll move it out of the way a bit. I'm scared to connect it up. It might go boom. Oh, you know what? I'm gonna get a resistor. Hang on a minute. I've got a resistor somewhere. Kicking about. The reason I'm nervous is I'm worried about the ESD damaging my circuit board, right? Because the pulse, yeah, it's a big pulse. But when normally when it goes through the MOSFETs, it's buffered at this end, but this is not buffered. I mean, the MOSFETs I've got chokes and, yeah, you know what I mean. I'll stick these resistors on here. I think these are 1 ohm. 1 ohm. I think there's 2 1 ohms in series. That's 2 ohms. Alright. Right, we're going to touch that capacitor lead. Ooh, you stay on there. It just sparked. It wasn't a big one. Right, because it's through a resistor. Now let's connect this up. Right, let's check voltage across it before we switch it back on. Yeah, so now it's got 29 volts. Let's move this back a bit. We now have, oh, you know what? I need to find my clips. You know my, yeah, just a minute. Right, I've got my nice crocodile clips here. We're going to plug these in. Like this. I'll connect this one. Oh god. You know what? When I click this on here, there's not going to be any room to click that little one on. Alright, let's try something. I'll take it off a minute. Clip that on there. It didn't want to stay on. How do we get this, the little one on now? Huh? Just a minute. Put the little one back on again. The big one should go over the top. I don't want to crush it. I'm trying not to crush anything. See if I can get this big one over without breaking anything. Can I get that on top? No, I can't. Can I get down there? No. This is marvellous. I can't do it. I'm going to have to... Oh, you know what? I've got another idea. Right. Let's forget about them frigging clips. And let's get some wire. The voltage has dropped sufficiently on here now that it's safe. Just get some wire. Take these out. Shit. That made me jump. These freaking Chinese clips are useless. Right, hold on a minute. Right, I'm just going to use some wire. So I've got some wire here, right. Just cut a bit of wire off here. This wire's so old it's gone dry. It's gone very dry. It's not brittle, but it's dry. So I'll find out. I think I've had this wire for 30 years, I'm not sure. Maybe 20. No, I think I've had it 30 years. There's no wonder it's freaking dry. I'm just gonna, it's solid core wire, so it's not a big deal. Right, there's no strands to flake off. Right, oh, catching my stand. See why I hate working with my camera sticking in my face, because it blocks my view. Right, so that end is going to be connected to this end. I need to trim this a bit shorter. Right. I never actually had any wire strippers. I got used to using scissors, you know. You can feel it when you hit the metal. You just stop when you feel that you've hit the metal. Right, let's connect this. So negative is on the far end, yeah. Turn this up a minute. Negatives on the far end. And we get this in the hole. Is it in? Yeah. Is that one in? Yeah. We're tight. Okay, those two wires are in. So now I can wire this around the terminal. And just wrap it around. Them clips, you know, they were I've lost my, you know, my old tweezers I had, my really old tweezers, they fell apart on me again, and I got sick of repairing them, and so I'm going to have to use my pliers to wrap that around here. Wrap it around, it's called wire wrapping, so you won't be able to see very good. Original electronic radios and everything, everything was wire wrapped before they used solder. They wrapped wires around everything. That's how they used to make radios, with wire wraps. try and get this on here. This is tricky, you know. I'm going to have to try and figure it out. When I take this off this capacitor and put it on a new one, there's going to be a spark in a minute. I can see it coming. Just wrap it in. Right, I've got positive on, negative on, and that one's fallen off, which is typical when you're wrapping wires. But the idea is I'll put it on, then those clips should hold it. Right, so clip is on here. Freaking heck. Oh, I've got you on, right? No, I haven't. It's not in the hole. It's... I cannot see what I'm doing. Right, is that on? These bloody wires, they keep hooking on my, you know, my stand. It's got these little adjustment things on them, and my wires keep getting snagged up on. Just a minute. This is nuts. I'm going to untwist everything. Right. Just a minute, let's get this one on. Can't see what I'm doing. Right, that's on. See if I can get the red one on. Put it back on. Turn my meter back on. I can't get in. I have a small one somewhere, you know, smaller clips from my multimeter, but I cannot think for the life of me where they are. Okay, it's on, look. We've got a voltage. Is this going to stay on there? I have no idea. It might fly off in any second. Alright, let's connect the power. See how well this bad capacitor, see what the voltage is. The leak down voltage. We'll see how far it charges up. And, right, let's switch that on now. Ooh. If it's high impedance, it'll probably charge up quickly. And it'll probably discharge quickly. But I've got 500 capacitors, well, 1000 in series, which is 500 microfarad, across this. So we're going to have anomalous readings. The only way to measure this properly would be to disconnect it from that end and see how fast this end drops. Well, look at that, it's got 82.2 volts and it's still charging. But some of it's due to these capacitors here charging, right? The big ones. Oh, I've knocked it off. My meter disconnected. Right. So we're seeing it charge. So it's peaking at about 82.1, so that's actually interesting. Now the other capacitor, the new one, which is this one, I expect to see a little bit of reforming going on with that because it's been in storage for... I could see a date code on it, and it looks like these new capacitors were in storage since 2005. That's a hell of a long time. So they're not exactly new, they're actually new old stock. So this capacitor has been in storage since 2005. I saw a date code on the receipt. Interesting. The best way to check how fast this discharges, this old one, is to pull one of the wires out. I'll probably pull the negative out. Where's my screwdriver gone? There you are. Right, so if I pull out the negative wire without, I'm going to block the view, damn it. I use my pliers. I want to see how quickly it discharges, because I want to check the leakage. I'll have to watch this video, this live stream back later and count how many seconds it takes for it to go back down. Right, if I loosen that screw, pull it out. Oh, my meter's come loose. There we go. Oh, you stupid. It's freaking late at lead. It's freaking lead. Right, 81, look at this. This is the voltage just across that capacitor. We're looking at leak down. The meter's going to use power from it, right? The meter's going to pull it down slowly. I'll turn this off a minute. Circuit off, because I don't want to zap myself. So we need to count how long it takes for this to drop down to whatever. So I want to do the same leak down test, internal leakage that is, you know. But obviously the meter's going to pull it down a bit as well. So I'm thinking that the newer capacitor is going to drop faster, because it's not being reformed. It's not being reformed. It's been stored a long time, so it's probably going to drop faster, which means it's got a higher impedance. I measured it on the ESR meter. You know, this digital, obviously I have to discharge the capacitors before I actually connect them back to this, but this ESR meter showed me the ESR is better on the new capacitor than the old one. It had a loss, percentage loss of 1, right? The old one had the percentage loss of 1%, and the percentage of loss on the new one, I think was I can't measure it now because it's got, well, we're going to have voltage in soon. I've got to discharge them before I do that. But I think the new one had a percentage loss of, I think it was 0.4, 0.5 or something, whereas the new one had a percentage loss of 1, which means that the new one is very lossy. Oh, I have no idea how long this is going to take. Electrolytics are well known for being leaky. I really should have tested it with a resistor across it, you know. Like, I'm probably going to have to do that, because this is going to take too freaking long. But that's not the point. I don't want to put a load on them. I want to see how leaky they are, and you can't determine that by putting a freaking resistor across them, right? My ears are buzzing. Somebody's swearing at me somewhere. So, oh my God, is that the time already? Oh, what? Oh my God, time flies. It's already freaking 9:30. Well, 9:20 p.m. I need to go to the store soon, so I'm probably going to have to do part 2 of this or something. There's a huge lag on this, you know. I'm looking at my meter and it's a 66.4, but look at the screen, it's a 66.9. So I don't know how long that lag is. It's terrible. So I'm now looking at my meter and it's a 65.5. Now it's a 66% on the screen. So that's how far out the audio is. The delay. I tried to resync the audio on the Streamlabs on OBS. I tried to set it by 500 milliseconds slower, but it's not milliseconds I want, it's freaking seconds. It's more like 2 seconds out of sync. That's 2000 milliseconds. There's 1,000 milliseconds in a second. So I've been having a lot of problems trying to resync my audio because it will not let me type minus 1000 or minus 2000 milliseconds into my OBS. It will not allow me to do that. That's why I can't get the audio synced. The only way to do it is to download it when it's finished processing by YouTube, re-edit it and shift the audio timeline, shift the actual audio soundtrack back 2 seconds, whereas the video stays, you know what I mean, where the video actual doesn't move. I don't know why it's out of sync. It shouldn't be. Because the video and the audio are travelling from my phone at the same time. Oh, this is ridiculous. You know what? I'm thinking it's better if I just wait until it gets down to 50 volts. Because it's going to take too long. So if I measure both capacitors down to say 50 volts from 82, we can measure that time. I'm not going to wait for it to drop down to, because there's less loss anyway at lower voltages. You know, for high voltage capacitor, it usually drops very, very slowly. That's why they put resistors across them in circuit boards. It's in circuit, like a 1 meg or 500 kilo ohm resistor to discharge them more quickly, because they take too freaking long to discharge. But you know, honestly, I'm going to have to do this test again at some point, but I'm not going to wait for it now because I've got other things to do. I'm just wanting to show you roughly how I would do this sort of thing. I also want to check that new one, see how quickly that one charges up. It's probably going to need to reform though. So let's see. Let's see. Right. Alright, I'm not waiting any longer. So this one dropped down to about 54, right? I'm not going to wait all night. So what is the voltage currently? I can't even check what's in there in these two, across these two 1000s, because I've got it connected to here. Unless I unplug it from there. Yeah, I could do that. I've actually got the positive lead though connected to that, so it's the negative lead I need. Alright, let's plug the negative lead. I want to see what the voltage is across this. That one's dropped to 14. So okay, this circuit is dropping faster than this, so I should have left it connected. It would have sped things up a bit. So that one's dropped to 14, look. Right. I should have left it connected. It would have been a much quicker test for leak down. Now if I connect it now, I'm going to see sparks, but bugger it, I'll do it. We're going to see this one drop more quickly. Let's see. Where's my screwdriver gone? There you are. Right. So we're going to see some, because this power is going to go back into there. I hope it's not going to destroy my circuit. Better not. It's probably going to dare. I mean, there's a huge voltage. Oh, it's only 30 volt difference. Let's try it anyway. Bugger it. Oh, it did it. Okay, it dropped it down. Right. It wasn't that big a... I think I might have a resistor in there anyway. Let's put this back in. I should have left it in circuit, you know. It would have made it quicker to time the circuit, how long it discharges. So that's already gone back down to 17 volts in there, and that pulled this down as well when I connected it back up. So, right, this is not an accurate test by any means. I'm just trying to get a rough idea what's going on with this old capacitor. Right, take this off here, take this off here. I need to connect the new one. These wires should come off. That one's off. Wiggle that one about. I did nip it on quite well. I can't get it off. Got ya, right. Take the old one off. I want to see what the new one's like. So, negatives at the top. Push that down if I can without breaking my freaking nail. Trying to wiggle it on. Let me get this on here. Where's my screwdriver gone? There you are. My other one. Push this down. Ooh. Can't see, my eyes are really bad. It's like studying the needle. I need to go to the store to get some bread. I've run out of bread. Right. Get these clips on. Negative. Let me get these damn clips on here. Is that on? I think so. Can I get the red one on? No. There's no room now. What? See, I have to get the narrow end in. Ah. Stay. Stay. Ah. I have some other clips and I can't find them right now. I'll rest that higher up. Let's see. I can rest it on somewhere. Oh, this is a bottle of these clips are very poor. They're designed for batteries. Can I get it round here? Stay on. Get this one on. Ah, the other one came off. Shit. Stay on. We're on right now, look. See the voltage. Okay. Are you going to stay? I'm not going to touch it. I'm just going to turn this thing back on. Now this might take longer to charge. Not that long, it charged up pretty fast, 82 volts. 83. So it doesn't really need to reform by the looks of it. It's going to discharge faster though, because I'm going to leave that wire in this time. I'm not going to pull it out. So it's going to discharge. I have to do this test again. I want to see how high it climbs up to. Seems to be. Yeah, that's a sign that it's reforming, because it's starting to drop a bit, the impedance. If you're wondering why I want to charge this capacitor up, it's because I want to measure the ESR after I've discharged it. Obviously, you've got to discharge your capacitors after you've charged them up. But I want to charge this up, get it up to about, well, 80 volts anyway. And I want to measure the readings, the capacitance and the ESR after it's done a little bit of a reform, right? Because it will reform slightly, because it's been stored since 2005, so there'll be a slight reform. But the old capacitor didn't need to be reformed because it was in use recently. A few months ago it was in use and it died. Yeah, the circuit just died. So it's lost its electrolyte. But the new capacitor definitely needs a little bit of a reform. A little bit, just to see if we can get good readings for the microfarad and the ESR. Can't say it properly. No, we're going back up again now. 83. There's definitely something. There's definitely some sort of reform going on here. If you remember, this circuit, I built uses a 555 timer and a diode pump. It uses a diode pump to generate the 80 volts. It basically oscillates through a bunch of resistors and capacitors to triple, well, double, triple, then quad, then sextuplate. I think it's sextuplate or something. It's 6 times anyway, and then 8 times and then so on, and until you get to the voltage that you want output. So the actual impedance is pretty high, so you get a really good accurate indication of how leaky capacitors are by the fact that the slightest leakiness of an electrolyte should show up on what maximum voltage I can see on here on the meter. So if you've got a short circuit capacitor, partially short circuit, it would show up definitely on here. It would pull it down quite a bit, and it would start to get hot. You know, the capacitor, it wouldn't get really hot, it would get warm because of the higher impedance. But so I am seeing some fluctuations on here, which I don't think I saw that on the old one, because the old one was already reformed, but this one definitely needs some reform. My brain didn't work like it used to do, so there's such a lot of stuff I've forgotten about, and things come back to me eventually, and I think, I forgot about that, you know. This H bridge is currently working at a very low frequency, by the way. It's currently working at about what? Probably 3 hertz or something. It's switching the output on these the purple and red wires. Oops, shit, I've knocked the lead. Don't you dare fall. I hope it's not going to fall. Break the connection. It's all over the place, isn't it? Going up and down, up and down, up and down. Sometimes it looks like that LED stopped flashing. It hasn't. It's just that the video capture, the shutter speed is mismatched with the pulse frequency of the LEDs. So sometimes the LEDs will flash. One LED will flash on when the shutter's closed, so it looked like it's not flashing, but it is. They are constantly flashing on and off. So, before this thing goes sideways, I'm going to switch it off and see how quickly it drops down, and switch it back on again. Right, I'm going to disconnect the battery now, see how quickly it drops. Should drop faster because I've left it in circuit with the, I think there's a pull down resistor in there maybe, or it'll leak down through some of the other capacitors that are in the circuit. See how quickly it drops. and I didn't do it exactly the same as the other one, so it's going to be different output, a different time scale, but this is a stronger capacitor, so in theory it should take longer. Unless it's reforming and there might be some leak down. Internal impedance, resistance, whatever, because they take a while to reform, you know. Usually it doesn't take that long. If they've gone past your short though, once they've done that, oh, it can take a long time, because Shango 066, he's done a lot of this high voltage reforming capacitors on TVs, and from his videos you get a very good idea how long, because he does a light bulb test. He runs stuff through a light bulb in series, which is a great way of doing stuff, you know, for safety, because if anything was to go totally short, the worst thing that could happen is the light bulb would come on really bright and you'd know you've got a fault. So it's a bit of you know, that old cartoon where the characters are running around and the light bulb pops above the head. It always reminded me of those cartoons, you know. Good little bit of safety is using a light bulb. And look, we're already at 50, we're already down to about 50 volts now, 50, yeah. We're already down to 50 volts now. So I need to do that test again with the bad capacitor. Because I know the ESR on the bad capacitor is not good. It has a loss of 1%. Whereas this other one has a loss amount of, well, I think it's 0.5 or 0.6, I'm sure. It's a lot less lossy. But for a capacitor that might need to be reformed, you would have expected it to be higher than that. So maybe it doesn't need to be reformed, but this is what I'm trying to figure out. I'm just trying to figure this stuff out. I do know for a fact that the old capacitor is gassy because it's bulging slightly. If you look at the dome on it, look at where the light reflects off it, you can see that it's shiny on the top right in the middle there. It should be equal all the way across the full flat surface, right? But there's a slight dome on it because it's pressurized inside. You can see it slightly. It's slightly domed. That capacitor was on the verge of blowing. As in popping. I am curious how much power is left in this one, because I'm going to do another test later on. I'm going to leave them standing on my table and I'm going to come and measure both the voltages on both these, this old one and the new one, see how much voltage is still left in them, because now they'll be self-discharging on just their own internal resistance, you know. They'll be, because there's nothing else there to pull them down now apart from themselves. Right, okay, we're already well below 50 volts anyway, so I'm going to disconnect this thing now. Let's see. Ooh. Right, get them off. I need these wires off here. Right, I don't want to short these out. Pull them apart so they don't short out. Right, so if I measure just that capacitor and the old one, they're going to be different readings right now, because the old one, I think I pulled it off, I think it's around 50 volts or something. So let's see what's in here now. No, it's got some. Oh no, it's because I connected it up, didn't I? So it pulled it down to 17 volts. That's right. So it will show 17 volts. Right. So that's got 17 volts in it. The new one's going to be around 40 somewhere. Yeah, 28. You know what I should do? Is connect these in parallel so they equalize, so that both capacitors have got the same voltage in. So what I'm going to do now, I'm going to connect both negatives together, right? Both negatives, and I'm going to connect both positives together so that they both have the same voltage in them. Ooh, if I can do this right. Right, hold them together while they equalize. Now both these capacitors should now have the same voltage in them. Let's see which one's the leakiest. That's got 22.4. That one's got 22.2. So the new capacitor has gone lower than the old one. So I expect something like that, because this newer one will be, as I say, it's probably got more impedance on it, a lower impedance on it, because it's been stuck in a drawer for like what 2005, let me think, 2015, 2024, about 20 years. Oh my god, this thing's been stuck in a drawer for 20 years. Right, it's, what's it measuring now? 21.8, 22.3. Huh, that's interesting. The old one's got more voltage still in it. Anyway, I'm going to put them aside. I'll equalise them again actually. Both negatives together. Both positives together. Give it another check. .8, 21.6. So the new one seems to be dropping faster than the old one. But I think that's probably right, because this will have a lower impedance. This has gone gassy, so that will probably die quicker though. You know, it's got higher impedance on it. Probably took the voltage quick, but it won't have the current. Won't have the amount of current delivery than this one. This one took longer to charge because it's got a low impedance. Check it again. 21.8, 21.1. Right, I'm off because I've got to go and get some bread. Freaking neck. My bread's been in the fridge and it's dried out on me. It's gone horrible. I like some fresh bread for my sandwiches. Right. See you later.